In this video, we solved problems 1 and 2 from the differential equations quiz number 5 from the spring 2021 semester. There were 3 versions of this quiz, and these are the versions of the problems that appeared, or these are the problems that appeared on version 3. Problems 1 and 2 cover the method of undetermined coefficients. Now, the first problem, you're not actually asked to solve the differential equation. You're asked to use the method of undetermined coefficients to find the appropriate form of y sub p, particular solution. We do not want to solve the differential equation. You don't have enough time. And we don't want to find y sub c. Although usually we would find y sub c, we would look at the form of the right-hand side, we would find a y sub p based on the right-hand side, and then we would modify our y sub p based on the terms in y sub c. But we're not going to do that this time. It's going to take too much time. Instead, we are just trying to find the y sub p that we would initially guess, that first guess before we modify it, for this right-hand side over here. So y sub p will equal, well, it'll equal a sum of a number of terms, and those terms will depend on the terms up here. Now, since I've got a negative 6x to the fourth plus 2x squared, like those are terms in a fourth degree polynomial. So I would guess that y sub p has a fourth degree polynomial in it. So we'll have ax to the fourth plus bx cubed and so on. You don't just use the x to the fourth, you want all of the terms in that fourth degree polynomial. And that's going to take care of these two together. We don't need a separate one for this because these are terms in the fourth degree polynomial as well. Now here I've got an exponential e to the negative 2x times cosine of x. So I would guess a constant times e to the negative 2x times cosine of x, because that's what I have here. But whenever I take derivatives of cosines, I get cosines, but I also get cosines from taking derivatives of sine functions. So anytime you've got a sine or cosine up here on your list, you also need the corresponding guess, but with a sine instead of a cosine. So we'll have g times e to the negative 2x times sine of x here. Here I have a constant, times sine of 2x. So I would guess that we'd have a constant times sine of 2x here, but derivatives of cosine of 2x also lead to sines of 2x if we take the right number of derivatives. So we'll have h times sine of 2x plus I times sine of x. Of course, I is not the identity, d is not the differential operator. These are just letters A, B, C, D, E, F, G, H, and I. 1, 2, 3, 4, 5, 6, 7, 8, 9. So if we were actually solving this differential equation, we would take the third derivative of this, we would substitute into the left-hand side, and we would set the left-hand side equal to the right-hand side. And then because of the linear independence of the functions on the left-hand side and the functions on the right-hand side, we can set corresponding coefficients equal to each other because of linear independence. So what that's going to do for us is it's going to give us, what did I say, 1, 2, 3, 4, 5, 6, 7, 8, 9. It's going to give us 9 equations and 9 unknowns. So that's why I would never ask you to do this without a computer or something like that to help you solve those 9 equations and 9 unknowns. But we could easily do this in something like Mathematica. We could plug this in, we could solve the 9 equations and 9 unknowns, we'd find the a through I, and then we could substitute those into our y sub p. And of course, the general solution would be y sub c plus y sub p. Now in problem 2, we're actually asked to solve the differential equation. It says find the solution of the non-homogeneous dE, but I guess we should be more specific. What we really want is a general solution. And we want to use the method of undetermined coefficients. Now, since it's non-homogeneous, the first thing that we need to do every time is we need to solve for y sub c, or alternatively, you can say solve the corresponding homogeneous equation, because the form of y sub c affects the form of y sub p that will actually work. So we always want to do that first. Now, the corresponding homogeneous equation looks just like this. On the left-hand side, but the right-hand side is 0. Since the corresponding homogeneous equation has constant coefficients, we're going to let y equal e to the mx, and then find the values of m that cause this function to satisfy that equation. Since it's a third-order differential equation, we'll take the first, second, and third derivative of that function, and then we'll substitute those into the differential equation. And that's going to lead to an algebraic equation involving our variable m. We want to find the right values of m so that the algebraic equation is satisfied. If we can find the values of m that solve that algebraic equation, which we typically call the characteristic equation after simplification, those are the values of m that cause y equals e to the mx to solve this. So that's the plan. Let's do it. Going to let y equal e to the mx. Then y prime is e to the mx times the derivative of the inside, which is an m. You take the derivative again, you bring the m down. Derivative of e to the mx is e to the mx times the derivative of the inside, which is another m. Bring your m squared down because that's a constant. Derivative of e to the mx is e to the mx times another m, the derivative of the inside, so we get an m cubed. Now, we're going to substitute these into the differential equation. Will no longer be a differential equation, it'll just be an algebraic equation. If y satisfies this equation, then when I substitute in y double or y triple prime, y double prime, and y prime, that should be satisfied by the values of m. So we will do that now. Y triple prime is m cubed times e to the mx. And we're subtracting 5 times y double prime. And then we're adding 6 times y prime. And I didn't leave myself enough space. That has to equal the right-hand side, which is 0. Now, all of these have an e to the mx in them, so we can factor that out. And we're left with m cubed minus 5m squared plus 6m. Now I've got this times this equals 0. The only way that a product is 0 is if one of the factors is 0. And since our exponential is never 0, we'll have this cubic polynomial in m must be 0. Let's factor that as much as possible. Notice that we have a greatest common factor of m. M times m squared gives us m cubed. M times negative 5m would give us negative 5m squared. And m times a positive 6 would give us that last term. And then we've got something quadratic that factors quite easily. I need two numbers that multiply to give me 6. Positive 6, so that they're going to have the same sign. And they have to add to 5. Add to negative 5. So negative 3 and negative 2 will work. Negative 3 plus negative 2 is negative 5. Negative 3 times negative 2 is positive 6. So that is our factored characteristic equation. This is the characteristic equation, and that's the factored form of it. And then we want to solve that characteristic equation for m. So we'll have this factor equals 0, which implies that m equals 0. Or this factor equals 0. When m minus 3 equals 0, that means that m is equal to 3. When m minus 2 is 0, that means m is equal to 2. So it turns out we have distinct real roots this time. m1, m2, and m3 are 0, 3, and 2 respectively. Now, because the differential equation was a constant coefficient equation, the corresponding solutions are just given by this e to the mx, where m is equal to 0, 3, or 2. So y1 is e to the 0x, which is of course just 1. And y2 is e to the 3x, which doesn't simplify, and y3 is e to the 2x. And then the general solution of the corresponding homogeneous equation, because we're eventually going to solve a non-homogeneous equation, is this. Since it's third order, it'll be c1y1 plus c2y2 plus c3y3. And y1 is 1, y2 is e to the 3x, and y3 is e to the 2x. Okay. Now we want to solve the corresponding, or we solved the corresponding homogeneous problem. Now we want to solve the non-homogeneous problem. So we'll write that differential equation down and we'll make an educated guess for the form of y sub p based on the form of the right-hand side of the differential equation. So I've got a constant here. So I would guess that y sub p has a constant in it. And then I've got a constant times sine of x, so I would guess a constant times sine of x. Now, this is my initial y sub p guess, but I always want to compare the terms on this list to the terms on this list. So I say, okay, do I have just a constant on this list? And I do. If y is just equal to 1 or c1, well, that satisfies the corresponding homogeneous equation. If I take the derivative of a 3 times and I substitute in, I'm not going to get 8, I'm going to get 0, because this is a solution to the homogeneous equation. So I need to bump it up. I need to multiply by an extra x. Then I ask myself, is ax on this list? It's not, so that's probably a good guess. Then I ask myself, is b times sine of x on this list? And it's not. And oops, I almost forgot, this is 2 times sine of x. So I get b times sine of x plus c times cosine of x in my y sub p, because derivatives of cosine could lead to sine and derivatives of sine could lead to sine. So to sine functions. So we have our educated guess for y sub p. Now we want to find the values of a, b, and c that cause this function to satisfy this differential equation. Well, in order to do that, we need to take a few derivatives. So I will compute y sub p prime. The derivative of a constant times x is just our constant. Bring the b down. The derivative of sine of x is cosine of x. Bring the c down. Derivative of cosine of x is negative sine of x. It was a third order differential equation, so I need to compute the second and third derivatives as well. Derivative of a, derivative of constant is just 0. Bring your b down. Derivative of cosine of x is negative sine of x. Bring your negative c down. The derivative of sine of x is cosine of x. It's third order, so we need one more derivative. Bring your negative b down. Derivative of sine of x is cosine of x. Bring your negative c down. Derivative of cosine of x is negative sine of x. A negative times a negative will make that a positive. Okay. So we've computed our derivatives. Now we want to substitute into this differential equation and set the result equal to this 8 plus 2 sine of x. I prefer to add vertically here because it makes the bookkeeping a little easier. Maybe for this particular problem, it's not necessary, but in general, it's a good idea to evaluate this left-hand side sort of vertically. Like, remember in elementary school, you would say 5 minus 3 is 2, and you would write it like this. We're going to do the same thing here with y sub p triple prime, negative 5 times y sub p double prime, and 6 times y sub p prime, because again, it makes the bookkeeping easier. Then we can put like terms in columns. So I've got y sub p triple prime, minus 5 times y sub p double prime, plus 6 times y sub p prime. And that's what I'll have right there. Okay, y sub p triple prime is this. So I'll put my cosines in this first column and my sines in my second column. Then I want negative 5 times y sub p double prime. Negative 5 times this is going to give me a negative 5 times a negative b is positive 5b times sine of x. That goes there. And this times a negative 5 is going to give me a negative times a negative positive 5c times cosine of x. And I'll put that with the cosine column, or in the cosine column. Then I want 6 times y sub p prime. Well, the 6 times the a, well, that's not a like term with anything else, so it goes in its own column. Then I'll have 6 of these cosines, 6b cosine of x. And then negative c times 6 is going to give me negative 6c times sine of x. We add these together, and we get 6b minus b is 5b. So we end up with 5b plus 5c times cosine of x here. And then I have 5b, and then c minus 6c. I put c6, but you get the idea. Multiplication's commutative. It's a little different, but it's fine. C minus 6c is negative 5c times sine of x. And that we're adding 6a to that. So that's the simplified left-hand side. after we substitute into the differential equation. And we set the left-hand side equal to the right-hand side. And then we're going to equate like the coefficients of like terms. So the right-hand side had an 8 in it, that's a constant, so that'll go here. And it had a 2 sine of x, and it doesn't have any cosines, so I will just add in a 0 cosine of x. Now sine of x, cosine of x, and 1 are linearly independent functions. You can't take a sine and a cosine and add them together and get a 1. There's no way you can do it. So since they're linearly independent, the only way this left-hand side equals the right-hand side is if the coefficients are equal. The coefficients of the corresponding functions are equal. So the coefficient of cosine on the left-hand side has to equal the coefficient of cosine on the right-hand side. So we have 5b plus 5c must be 0. And then similarly, the coefficient of sine on one side of the equation has to equal the coefficient of sine on the other side of the equation. So we have 5b minus 5c, that has to be 2. And the constant term on one side has to equal the constant term on the other. So we have that there. So from this, if you want, you can subtract 5c from both sides and then divide by 5. You get b equals negative c. Here, you could substitute in negative c for b, and then you'd have negative 5c minus 5c is negative 10c equals 2. So c equals negative 2 over 10, or negative 1/5. And b is the opposite of that, so b is positive 1/5. And from here, you have a equals 8 divided by 6. Divide the numerator by 2, divide the denominator by 2, and that's what you get. I mean, that's one way of doing it. I use the substitution method. You could have also added these together, and then you would have found that 10b equals 2. So b would equal 2 over 10, which is 1/5. And once you had b, you could use the equation to find c, one of those equations to find c. Okay, so these are the values of a, b, and c that are required for y sub p equals this function to satisfy this differential equation. So we just substitute those values of a, b, and c into the form of our solution y sub p now. So y sub p was a times x, and a turns out to be 4/3, plus b times sine of x, and b was 1/5. Oops, it's sine. Plus c times cosine of x, and c is negative 1/5. So adding a negative 1/5 cosine is the same as subtracting 1/5 cosine of x. So that's our y sub p. We set the left-hand side equal to the right-hand side. We had a system of 3 equations with 3 unknowns. We solved for a, b, and c. And then we used that to find y sub p. We substitute into the form of y sub p. And the general solution just comes from taking y sub c and y sub p and then adding them together. Don't forget to label it with a y. The general solution is y equals y sub c plus y sub p, which in our case is c1 plus c2 e to the 3x plus c3 e to the 2x plus y sub p, which is this function. And these will all work for all real numbers. So on the interval from -∞ to ∞. That'll do.